Kinetic, as you know, refers to the motion of an object. If we assume that the particles that make up matter are moving in a continuous random motion, we can extend that to a lot of the properties we observe. We can go from talking about a huge amount of particles that make up the mass and volume and pressure to looking specifically at what causes those properties. We use gases in our explanation because the particles are very spaced out and tend to behave in a manner that is easier to observe and explain than liquids and solids. But first we need to set up some assumptions about the gases in order to explain their behavior. First, we need to be dealing with a large number of particles. Then we need to assume that the particles themselves have no volume. We call these point particles. We also need to assume that we are dealing with a pure substance and that the particles are all identical. This has to do with the mass of each particle, which we will soon see. The particles also collide with each other, and these collisions are random and follow along with Newton's laws. We also want to assume that the collisions are elastic and that there's no energy lost in those collisions. If we take a particle moving inside a box, that particle is moving along at some velocity in the x direction. We can then say that the particle has a certain momentum as it is moving, found by taking the negative mass times the velocity in the x direction. We use a negative in this case because the particle is moving to the left, and we have set up our coordinates so positive x is to the right. The particle eventually runs into the wall of the container and bounces back in the x direction. We don't care about the y and z directions at this point because it is the x direction that is perpendicular to the wall, and therefore the direction in which the force is acting. This particle is now moving in the positive x direction, so its momentum is found by multiplying mass by the positive x velocity. The particle has had a change in momentum, and change in momentum is found by subtracting the initial momentum from the final momentum, which ends up as 2mvx. Since ultimately we are looking at pressure, we want to figure out what force is being exerted on the wall of the container. And we know that force is the change in momentum over the change in time. And we just found momentum to be 2mvx. Here's where it gets tricky. The change in time is the amount of time in between collisions. So the particle moves through the container, bounces off of the wall, and moves back in the other direction until it hits the opposite wall. It collides with that wall and moves back, and finally collides with our initial wall again. So that change in time is going to have to do with how far the particle must travel and the velocity at which it is moving. From our kinematics equations, we know that the change in time is equal to the distance divided by the velocity. If we designate the length of our container as L, then the distance the particle travels in the x direction is 2L. So the change in time is 2L divided by the velocity in the x direction of the particle. So we plug this into our force expression and clean it up. Our 2's cancel, and we get Vx on top twice. So the force on the wall, or the force on the particle for the x component of one atom, is mvx squared divided by L. So we know the force exerted by one particle on the wall of the container. Pressure is another thing we typically want to look at. Of course, pressure is the force divided by the area, and when we plug that in, something interesting happens. Pressure is equal to mvx squared divided by the area times the length. This is just mvx squared divided by the volume. Now the thing to keep in mind is that this is the pressure exerted by a single particle, and one of our initial assumptions was that there are a lot of particles to deal with. So the idea is that not all the particles are traveling at that particular velocity. Some are going slower, some are going faster. At any given temperature, you have particles moving a certain range of velocities. Remember, temperature is the average velocity of the particles, so some are moving more slowly and some are moving at a greater velocity than the average. So we've developed a way to describe the probability of finding a particle at any given velocity. The green line represents particles at a high temperature. The red line represents particles at a lower temperature. There are, of course, some particles in the hot gas moving faster than the particles in the cool gas. But there are also some particles in the hot gas moving slower than some of the particles in the cooler gas. At the top of the peak of the red curve is the most likely velocity of any particle in the cooler gas. And at the top of the peak of the green curve, you most likely find the velocity of any particular particle in the hot gas. Looking back at our pressure equation, there are a couple things we need to adjust for. First of all, we know that we do not have just one particle in the container. We count our particles by number of moles, so we can multiply that expression by n. According to our graph, we also know that the temperature is a measure of the average velocity, so we would make a note of that in our equation as well. But we have also been reporting that velocity in terms of the x component only, and really it is important to consider the y and z directions as well. So the total average velocity squared is equal to the average velocity in the x direction squared, plus the average velocity in the y direction squared, plus the average velocity in the z direction squared. What is even more interesting here is that the velocities in each direction are random, which means they are all equal to each other. So the total average velocity is 3 times the average velocity in any direction. Another way to write this is the average velocity in the x direction is equal to 1/3 the total average velocity squared. This gives us something to plug into our pressure equation that doesn't just take into account one direction. Now, you didn't think we were done, did you? Because if we look closely, we see there is an expression with the mass times the square of the velocity. This is actually 2 times the kinetic energy, right? So the pressure is equal to 2/3 of the number of particles divided by the volume times the average kinetic energy of the particles. Now remember back to our discussion on the ideal gas law. We had the pressure times the volume equal to the number of particles times Boseman's constant times the temperature. Look at both of those equations for a second, because we have now related those microscopic particles to the macroscopic properties that we observe. So Boltzmann's constant times the temperature of the sample is equal to 2/3 of the average kinetic energy of a particle. We can also express this in terms of the average kinetic energy of a particle in a gas. This is essentially the definition of temperature. So what is the average kinetic energy of a gas molecule at 20 degrees Celsius? Well, the only thing we know is the temperature. That is really all we need to know if we need to find average kinetic energy. The only thing to really note is that we have to convert the Celsius temperature into Kelvin. Once we do that, plug them in and we find 6.07 times 10 to the negative 21st joules. This is really a really small amount of energy, but if you think about it, you're talking about a gas particle. So it does make sense that the energies are going to be significantly smaller than the larger objects.